Okay. And welcome. Hopefully you can hear me. Hopefully you're comfortable. So, sort of a lot of math to do today, I think. We're going to talk about collisions mostly. I was going to do last day of just sort of slamming on the brakes thing. This is a conservation. This is not a collisions one. But if you lock all four wheels, that you have the coefficient of kinetic friction. So, and you would know it because your car would be making this enormous screeching sound as you were slowing down. So, personally, that's never happened to me. I feel like my mic is weird. Yeah, it's cutting in and out. Yeah. The battery thing, maybe? No. Try the other mic. Replace it. I'm gonna switch mics. How is this one? Let's see how it holds out. Locks all four wheels. So I'm going to call the system here is, I guess, car plus road surface. We talked a little bit about this before. If you end up with some internal energy on the right-hand side of this energy conservation equation, then you're sort of including the road surface, I guess. So the initial situation, is you've got a bunch of kinetic energy in this car. Whoop. Terrible car drawing, but there's the wheels. And you don't know what the initial speed was before the collision. And then, or not before the collision, before the slamming on brakes part, the screeching part. And then what happens is that it goes like that until over here, same car, final, V final equals 0. And there is this, I'm going to put kind of like the steam coming off of the coffee or something like that. Delta U internal is like the heat, if you get it. And then this distance here, D, is equal to 18 meters. And so, I don't know if you want to draw out the things, but kinetic energy, initial, plus some work is kinetic energy final, plus some U internal. And I'm going to set the work equal to 0. So if you wanted to draw energy bar diagrams, this gets converted into this, the heat. So the way it looks like is 1/2 mv initial squared. I'm a little worried because we don't have the mass. So when I don't have the mass, then my hope is, I sort of cross my fingers, that it's going to cancel at the end. So I'm just going to write down m, and maybe it'll cancel out. Plus 0 equals 0, final kinetic energy, plus F sub k times d. So that's that U, delta U internal is always positive, like the magnitude of the friction force, times d. And we have an equation for the friction force. The car free body diagram looks like this. You've got the normal force, you've got mg, and yeah, I bet that's where the m is going to go away from. And then you've got the kinetic friction force. The sum of all the forces in the y direction is equal to 0. That's equal to n minus mg. So that means that n equals mg. The sum of all the forces in the x direction is going to be negative kx, if you put x that way. Define x to the right and define y to be plus. So that's it. So that's just equal to m times a sub x. So I would say that f sub k is equal to mu sub k times n. And we can, now we have from balancing the y forces that it's going to be mu sub k times m times g. So actually, I think that's all I'm going to do. I'm going to plug that into this equation. Take this and go plug it into there. So I've got 1/2 mv initial squared equals mu sub k times m times g times d. And I was right. The m's cancel. Whoop. So that's lucky. And now just solve out for vi. So vi is going to be, there's going to be a 2 mu sub k times g times d, and then the square root. I don't know if that's me hissing. Okay, so we can plug in square root of 2 times 0.8 times 9.8 times 18 meters. And take the square root, and I get 17 meters per second. Was the initial speed before you slammed on the brakes. Okay. So this is something I guess I could have solved using Chapter 4 stuff and forces and acceleration, but I decided to do it the Chapter 7 way, using energy. Okay. Either way is fine with me. Sometimes, so let's do another one. Sometimes energy is kind of the only way to do it, especially if you don't have angles and things. A small box of mass 10 kilograms is released from rest. So let's start listing our knowns here. Known. M is equal to 10 kilograms. An initial height of 2 meters on a frictionless incline as shown, and they don't give you this angle, right? So that's why I think you really can't use Chapter 4 methods to solve this particular problem, is because no one's told you what that angle is. But it's frictionless, so this H initial is 2 meters is going to give you what the initial gravitational potential energy is, and you can conserve energy, and it should work out. On a frictionless incline as shown, at the bottom of the ramp, it encounters a rough surface with length d equals 1 meter. So d friction or something like that is equal to 1 meter. And on that thing, mu sub k is equal to 0.25. And then a frictionless circular rise. At what height hf does the box stop on the circular rise? So it starts at some initial height. Probably it's going to lose some energy on the kinetic frictiony surface, and then it'll rise up to like a less height. And also, you don't know any of the angles or the curviness of this thing, so really, conservation of energy is the only way to solve this problem, I think. So if you define the system is the box plus Earth, I guess, because we're going to use MGH a lot, plus the surface, then delta U internal is going to be plus F sub k times d, will be lost along the sliding D part. And so K initial plus UG initial plus external work equals K final plus UG final plus delta U internal. There's a lot of ways of setting this up, but this is the way that the book likes to do it. I'm going to say here that there's no external work on the system. Because, and also, the box begins and ends at rest. So a lot of these terms are zero. So if you want to kind of do your this plus this equals this plus this plus this. So what I think is that there's no initial kinetic energy, and there's going to be some initial gravitational potential energy. But then what's going to happen if you maybe, I don't know how you want to divide this up, maybe make that 4 segments, then 3 of those segments are going to go in there, and 1 of those segments over there. Something like that. But basically, you got 0 plus mgh initial plus 0 is equal to 0 plus mgh final plus delta U internal, which actually, let's actually write that out. Fk times d, right? F sub k times d. Okay. And then once again, on the flat surface, we can draw the force diagram because we're going to need to find that friction. I think it's just normal is up, mg is down, and then you got Fk to the left. The sum of all the forces in the y direction equals 0. So 0 is equal to n minus mg. So n is equal to mg. And then I also got that the force of friction is equal to mu sub k times n. So that's mu sub k times m times g. So this equation here is going to be mgh initial equals mgh final plus mu sub k times m times g times d. And there's m's in every term there, so I can divide both sides by m. So that 10 kilograms turned out not to matter. And now I can divide both sides by g too. There's a lowercase g in every equation as well. Let's divide by g. So even gravity doesn't matter, which is weird. So I think I'm just left with h initial equals h final plus mu sub k times d. So, and we're finding h final is equal to h initial minus mu sub k times d. So it's equal to 2 meters minus 0.25 times 1, and you get 1.75 meters, which, as we expected, is a little less than 2 meters, as expected. This is a big thing they do in the book, is they call it the evaluate step. You kind of look at your final answer. I call it the sanity check. Does it make any sense? This one seems to make sense. If you got something bigger than 2, that to me wouldn't make sense because there'd have to get some extra energy from somewhere. Okay. We doing okay? Any questions? Okay, let's do a top hat question. This is on the, so there's collisions and explosions, and what's similar about a collision and an explosion is that they both happen over a very short time interval delta t. So if there are external forces, such as friction or gravity, the impulse from these external forces is negligible during the delta t of the collision or of the explosion. So this is an example of that. You got a firecracker, which goes psh, and quickly converts itself into a bunch of little fragments. And so you want to compare the momentum and the kinetic energy of the firecracker before the explosion to all those little fragments after the explosion. Just take a look at that. Maybe give you a couple minutes to think, pair, share. Think about it. Find a neighbor. Discuss what you think. I'll tell you what I think. Yeah, so that was the one that I liked as well, which is that, so let me write it out. So we got the note here. Is that I would say that during a collision or explosion, delta t is very small. So external impulse can be neglected. Or anyway, it's very small. So it's approximately true. Whoops, I left that. So what that means that P initial is equal to P final. I guess there might be gravity if it was flying up, and so gravity would have an external impulse, but it'd be pretty small if the explosion was really, really short. So that's why we say that the total momentum of the fragments is equal to the momentum of the firecracker. But the kinetic energy is completely different, and that is because there's a whole bunch of chemical energy inside the firecracker that changes into kinetic energy. That's the purpose of all the gunpowder that's in there. Okay. So kinetic energy increases a lot. Okay. So a collision is a process that occurs when two or more objects are in direct contact with each other for a short time interval, such as a baseball being hit by a bat. This is like during that collision. So you just hear a little click, but it must take some little interval delta t, which is small. And during that time, there's very, very large forces between the two objects. But if you define the system as being both objects, both the bat and the ball, then those are internal forces, so there's no external impulse from either force. And then, by actually measuring things, we can determine the amount of kinetic energy that's converted into internal energy. And you can't tell ahead of time how much kinetic energy is going to be lost to internal energy. In collisions where there's a deformation of the system, you can't really predict it. You can just kind of measure it, sort of like the coefficient of friction or something. There's a coefficient of restitution where you look at how much energy is lost depending on the type of object. So what we do, we don't know how to do something, is we classify it. So we've got three types of collisions. Elastic collisions, in which the momentum and the kinetic energy of the system are constant. So the internal energy does not change. And I guess it's sort of an ideal case. There's no perfectly elastic collisions in nature. Although if it's very rigid objects, such as billiard balls, they come kind of close. There's not much heat or energy lost. And also, subatomic particles, when they collide, those are quite elastic collisions as well. And then real collisions are inelastic, meaning that the kinetic energy of the whole system before the collision is a bit bigger than the kinetic energy just after the collision. There's some losses there. And then in physics we have this third, so this is a subcategory of inelastic collisions, is totally inelastic collisions, and that means that the objects stuck together. So if they have some original relative velocity, it ends up as being zero relative velocity. Should we go aux plate? I can show you on the video a bit, just these. We've got lots of basketballs and things like that, but lift that down for a sec. So this right now is set up so that there's these magnetic pushing. So the pushing force sort of goes up, they don't touch each other, and this approximates pretty well an elastic collision. So in an elastic collision, what's kind of interesting is that the initial relative velocity usually ends up to be the final relative velocity. So that's an example of an elastic collision. If they both go towards each other, then they just both bounce right off each other and go the opposite direction. If you want a totally inelastic collision, then you flip the magnets, and there's Velcro, so that the things stick together. And that happens a lot as well. So in both of those types of collisions, the momentum is conserved, but only in this case of elastic does also kinetic energy get conserved. Okay. All right. Laptop 2. Okay. Good. Let's do, I have 3 top hat questions where you're looking at some data in a figure. So it looks like this. So you look at the data and then try to determine, based on the data, which of these 3 kinds of collisions is it? Or is it a case where momentum's not conserved? That could happen, I guess, if there was some external impulse, which is usually you're supposed to neglect it, but I guess you could have an external impulse, maybe, that would screw things up. So is it either elastic, inelastic but not totally, or totally inelastic. So look at this. Just before the collision, you got a 2 kilogram moving to the right at 3 meters per second, an 8 kilogram moving to the right at 1.5 meters per second. Afterwards, you have a 2 kilogram moving to the right at 1.8 meters per second, and the 8 kilogram moving to the right at 1.8 meters per second. So I think they're stuck together. See what you guys think. 20 seconds, please, to click in for this one. Going once, going twice. Final answer, please. Okay, let's see what survey says. Guys, 318 answered. A lot of people are saying totally inelastic, which is the one that I like. So I give you this hint that if they end up with the same velocity, that means the final relative velocity is 0. So that's kind of like sticking together, although it looks like there's a big gap here. But the only thing we have to do is just check to make sure it's not D, which is maybe the momentum's not conserved. So let's do that, actually. Before, I've got the initial momentum is 2 times 3 plus 8 times 1.5. So that's equal to 6 plus 8 times 1.5 is 12, I think. So I got the P initial is plus 18 kilograms meters per second. And then P final is going to be 2 times 1.8 plus 8 times 1.8. So I definitely had to do that on my calculator. I got 3.6 plus 14.4. And luckily, it's also plus 18. So someone's worked out the numbers here so that they're the same. So that's good. So that's why I like this C. Same. Good. So what this means is that there's no external impulse changing the total momentum of the system. Impulse. Want to do another one? With more data. Ready? Okay. Same exact question, but now you've got 2.1 meters per second. So there are different mass blocks. A 9 kilogram block is moving to the right at 2.1. Hits a 3 kilogram block that's moving to the left at 0.6. And then after, there's all these other things. So they're both moving to the right at 1.5, actually. Right. This is going to take some calculation. Let's give you a minute to do that. Okay. Try to pick one. Now work this out on my numbers. No one's yelling at me, so let's just see what people say. So 80% are voting that you can't actually do this one. So let's do the momentum check. Here I've got 9 times 2.1 minus, so this is initial, one's going the backwards way. So I've got minus the 3 times 0.6. Because remember, momentum is a vector quantity. So you've got 18.9 to the right, minus 1.8 to the left. So I got plus 17.1 kilograms meters per second. And then finally, we've got 9 times 1.5 plus, plus 3 times 1.5. and I got plus 18. So it wasn't quite the same. So there must have been some kind of external impulse changing the total momentum of the system. So not the same. So collision impulse, which is weird. That usually doesn't happen in physics. Could happen though, I guess. And then last one of this kind, let's do this one. Same thing. Look at the data. Try to figure out which of the three kinds it is, or if it's possible. Not possible. So actually, I just decided to eliminate D by checking those momenta. So it's really one of the this is going to be no external impulse, which is a good kind of collision. So it's either A or B or C, I think. So how do you choose? What do you have to compute? Kinetic energy. Thank you, thank you. Give you a minute to do that. So, kinetic energy check. Oh my God. So K initial and K final. If that's enough time, let's see what survey says. Here. A lot of people thought it was elastic. The kinetic energy is conserved. Let's see what I think, actually. Laptop 2. So kinetic energy check is you've just got, they're all positive, right? So 1/2 times 4 times 1.8 squared plus 1/2 times 6 times 0.2 squared. So I got 6.48 joules plus 0.12 joules equals 6.6 joules. Okay, and K final is 1/2 of 4 times 0.6 squared. Sorry about the messiness here. That's supposed to say squared. Plus 1/2 times 6 times 1.4 squared. The directions don't matter because kinetic energy is just based on speed, plus 5.88. So I got 6.6 joules. So yeah, I like it. It's elastic. That's great. Okay. So well done. I'm going to do a couple more examples for you. So you kind of see how these things go sometimes on test questions. We have that term test 2 coming up. Let's say we've got 2 cars, both of mass m, they collide and stick together. So this is a totally inelastic collision. Prior to the collision, one car had been traveling north at speed 2v, while the second was traveling east at speed v. So again, neglect the external impulse. You can conserve momentum here. Immediately after the collision, what is the speed of the joined cars? And then, what's the ratio of the final kinetic energy to the initial kinetic energy? So how much has been lost? Has it gone down to 1/2? I guess 1 would be elastic, so I don't think it can be that. But 1/2, 1/4, 3/4, something like that. So let's see how I'd work this out. So I think you just use conservation of momentum. So you've got, let's define plus y is north. I'll put north as up. Plus x is east. We've got a bird's eye view of some car of mass m traveling. So the one traveling to the east is at speed v, and the one traveling north is at speed 2v. Okay, so that's like initial. And then finally, what will happen, I think, is that they'll join up. So they'll be going, they have these 2 crashed up cars, I guess m plus m, going at some final speed, v final, I guess. And so what you do is you do conservation of momentum. P initial x equals P final x. So m times v is equal to 2m times v final in the x direction. So So what that means is that V final of the things in the x direction is equal to V over 2. And then P initial y equals P final y. So you've got m times 2V is equal to 2m times V final y. And what that means is that V final y is equal to V. And then we can use Pythagoras. We have the two components. So I've got V final. Remember, it's sort of like this. Here's your V final. Here's your V final y. And here's your V final x. And here's a right angle. I don't know what the angle is, but I know that V final squared equals V, the component squared. And then you can take the square root, I guess. So V final x squared plus V final y squared. So it's going to be V times the square root of 1/2 squared plus 1 squared. So it's going to be equal to V times 1/4 plus 4/4. So I've got V. So V final is equal to V times the square root of 5 over 4. So I think it's E. Something like that. Got a symbolic answer there. And then if you want to do ratios of the kinetic energies, just figure out what kinetic energy initial is of the two objects separately, and then kinetic energy final, and just divide, and hopefully the V's cancel out. So you got K initial is equal to 1/2 mv squared plus 1/2 m2v squared, which is mv squared times 1/2 plus 4/2, which is mv squared times 5 over 2. And then K final is going to be 1/2 times 2m, because they're squished together, times the V final squared. And we already had that. It was square root 5 over 4, right? So it's just mv squared. The 2's cancel, I guess. You get m times v squared times 5 over 4. And so then you do K final divided by K initial. You get mv squared times 5/4. That's the final. Divided by mv squared times 5/2. And you get 5/4 times 2/5. 5's cancel. You get 2. You get 1/2. So like B. Okay. Just typical kinds of things that show up on these Chapter 7 test questions. We okay? Any questions? Okay. So the next thing I'm going to do is try to derive this thing. So elastic collision in one dimension when the ball 2 is initially at rest. So this is when you consider a head-on, perfectly elastic collision of a ball of mass m1 that has some initial velocity v1 initial with a ball of mass m2 that's initially at rest. During the collision, then there's going to be a bunch of stored energy, but after the collision, the final kinetic energy is equal to the initial kinetic energy by definition of an elastic collision. So all the energy gets released again. And then the final two balls have different kinetic energies. So there's two equations and two unknowns here. You've got momentum conservation and kinetic energy conservation. These are two equations. The two unknowns are the final velocities of the two balls. But you know things like the initial velocity of ball 1. You know initial velocity of ball 2 is 0 because you've set it to be 0. And you know the masses. These are the equations I got. I would say that these are good to put on the aid sheet. You can derive them pretty easily. I did it this morning. I'll show you to put on your aid sheet, I think. I'll display it in a second, but this morning I just kind of did this math. Sorry, it took a while. But basically, all you're doing is two equations, two unknowns. You have to kind of solve it out. There was a little bit of trickiness, but I got this equation, and I got this equation. Don't worry too much about it. I've posted it on the thing, but you get this. It works every time. And these equations are especially handy. They come up in physics all the time because you can always switch your frame of reference so that ball 2 is at rest. Because things are not accelerating very much during a collision, so you can just switch the reference frame in which ball 2 is at rest, get what the ball 1's velocity is in that reference frame, then use these equations, and then switch back in the end to the lab frame. It's a real handy trick. So we have this Astro Blaster. There's like three rubber balls stacked on top of a larger rubber ball. And what happens is if you drop them, it's hard to do. No. Let's do it with a tennis ball and a basketball. More fun. I'm going to try to, again, my hands are so shaky it's hard to do it. Whoa! It's supposed to go straight up. Let's try it one more time. Need someone with let's try it lower height. There we go. So, idea being, this is another party trick, that somehow during these collisions, so I guess the basketball collides elastically with the floor and reverses its kinetic energy. And then there's a collision between the basketball and the tennis ball that's kind of elastic. And that shoots the tennis ball way, way up. So we can try to work that out if we have time, which we do. Let's say you've got a 0.5 kilogram basketball and a 0.05 kilogram tennis ball, and they're stacked on top of each other and then dropped at some height, maybe 0.82 meters above the floor. How high does the tennis ball bounce, assuming that all the collisions are perfectly elastic? So this will be kind of like the maximum height it could possibly get. In real life, all the collisions would be a little less than elastic, but this gives you sort of an idea of how the math should work. So the way you do it, segment 1 is free fall. They both fall sort of together, and I can imagine maybe there's a tiny little gap between them as they're falling. Segment 2 is that there's an elastic collision of the basketball with the floor. So the way I like to do it is I think of it as the tennis ball doesn't know quite yet that the basketball is hit because of that little gap. Then the basketball is going up. And then segment 3 is that it's going to hit the tennis ball. And that's going to be when we're going to use those equations I just derived in a page and a half of math to see what the final relative velocity is during that collision. So you don't have the floor. And then you can see how high the tennis ball goes using kinematics again. Want to do it? Okay. So you're dividing the motion into segments. I think, the free fall things you guys can do, you can use conservation of energy or whatever way you want to do it. You end up with square root of 2gh, the final of segment 1, square root of 2gh. You guys know it. That's a square root thingy. And it's going to be down. And then the idea is that the basketball bounces elastically. So when you have an elastic collision, the kinetic energy just before and just after is the same. So the speed upwards is the same. And what's interesting is that momentum is not conserved when you collide with the floor. Because the floor is attached to the Earth, which has a mass of 10 to the 24 kilograms. And so I guess it probably does conserve momentum with the Earth, but the Earth doesn't move. It sort of absorbs out the momentum. So you end up reversing the momentum of the basketball, but keeping the exact same kinetic energy. So whenever you collide with something that is fixed to the Earth, then the momentum conservation is not there, because there's an external impulse from the Earth. Anyway, the kinetic energy is, so it's going 4 meters per second down, then it goes 4 meters per second up. Okay, this is the part where we're going to use that equation. Segment 3 is that you got a 0.5 kilogram basketball moving upwards at 4 meters per second and strikes a 0.05 kilogram tennis ball that's moving downwards at 4 meters per second. So what happens? Well, just find the tennis ball after the collision. What we're going to do is we're going to say initial. Here's 2. It's going V2 initial is negative 4 meters per second. And 1, the basketball, is going up with V1 initial is plus 4 meters per second. 1 is the basketball. And 2 is the tennis ball. And then finally, what we're going to have is that 2 is going to be going up with some V2 final, which we don't know. And then 1 will also be going up probably with some V1 final, which we don't care about. We're just trying to find the tennis ball. So what we do is let's switch to a reference frame in which the tennis ball is at rest. Two is at rest. That's easy. Just add plus 4 meters per second to all the velocities. And then remember to subtract those all at the end once we've done our math. Because this is in a new reference frame. When I get back to the lab frame, just minus those. So all we do is we say, so ball 2, rest frame. I can put little ticky marks to remind us that we're in this weird frame. V2 initial tick mark equals 0. And V1 initial tick mark is equal to 4 plus 4. So now the basketball is moving up at plus 8 meters per second in that reference frame. Now you just use the thing we want, which is this equation, which was on your aid sheet. V2 final, don't forget to put a ticky mark, is equal to 2 times m1 divided by m1 plus m2 times v1 initial ticky mark. So it's 2 times the 0.5 divided by 0.5 plus 0.05 times 8 meters per second. I plugged all in, I got plus 14.5 meters per second. That's the velocity of the ball in this weird reference frame, and then convert back to the lab frame by subtracting the 4. That's how we analyze collisions in particle accelerators. You switch to the reference frame of the target, then do your math, and then go back into the lab frame. So V2 final without the ticky mark is V2 final with the ticky mark minus 4 meters per second. And you get V2 final is plus 10.5 meters per second, which is still bigger than 4, and that's why it goes so high up. So segment 4 is that you've got a tennis ball going up at 10.5 meters per second, and it goes up to a height of 5.6 meters maximum. Mine went a lot less than that. So the balls were dropped from 0.82, but the tennis ball rebounded up to 5.6 meters, so it looks like energy is not conserved. So thanks for your patience. This is the lab you're going to be doing next week, actually. You're going to be doing conservation of energy stuff. So I'll send you an email about that with a little warning about some videos, depending on your role. Have a great weekend. See you Monday.